I'm going to talk about wearable technology and some of our research over the last few years. So, over the last hundreds of years, right, we've been wearing clothes, but primarily they've been focused on two major functionalities, and one is protection, and the other is aesthetics. And what we think going into the future is that if there's ongoing research as well as unmet needs for clothes that can do beyond just protection and aesthetics. Clothes that can sense, store data, analyze, and even communicate. And a lot of our research focuses on the sensing aspects of it, which is what I'll talk about in the next 5 minutes. So we've developed a patented process called electrophoretic deposition. In very simple terms, what we are doing is we are taking carbon nanomaterial, we are functionalizing it with chemicals, so they have, in this case, a positive charge, and it's dispersed in water. And then when we apply an electric field, these positively charged particles move towards the negative electrode and coat whatever is connected to that substrate. So in this case, we could have fabrics, we could have plastics, we could have composites. So we've done a variety of different work. For this specific talk, everything that we are doing is on fabrics, and it's with carbon nanotubes. So on the right hand side, you see a cross section of a polyester fiber. This is from a fabric from a t-shirt that I had bought from Target. And you can see that it forms a very uniform, nice, thick and porous conformal coating of on the fibers, right? So this is a roll to roll process that we've developed. We're doing it at room temperature and using water as a dispersion. So that gives us a lot of versatility in the different types of materials that we can coat. And here I'm just showing four of them, which is sorry, rayon, a blend of cotton and polyester, polyester and wool. We've done carbon fabrics, glass fabrics, aramid, and a whole lot of other stuff. We show here that we can do different types of microstructures. It could be woven, it could be knitted fabrics, or it could be yarns or single filaments. And you can see at the bottom image is the scanning electron micrographs of how this coating is thin and conformal, so it'll take the shape of whatever the base fiber is. And so if we are making a garment out of it, we are adding fractional of a gram of weight on it. Doesn't really change the feel or the properties of the fabric as much. Now, after coating, essentially what you're able to do is you're able to make it a piezo resistive sensor. What it means is that if there is any external load or deformation, the electrons that travel through these conductive materials, the contact resistance changes, and it can lead to a bulk change in the electrical resistance. So to simplify it, what we want to keep in mind is that if I stretch the sensor, then the electrical resistance will increase, and if I compress the sensor, the electrical resistance will decrease. But we are going to track electrical resistance for everything. So we've developed flexible pressure sensors, and these have an extremely wide range of pressure sensing capabilities. This is me just pushing on the sensors gently with my fingers. In the middle, you can see that I'm pressing on it with my body weight, and then we drive a forklift in a lab over it. And you can see how the resistance changes different for different amounts of pressure. Now, from a gate viewpoint, I'm collaborating with Jill Higginson in the biomechanics biomedical department, and we've done some work where we've walked on the instrumented treadmill in her lab. Here, I'm showing a couple graphs that show okay, if you're walking on the flat ground, you're able to capture the typical M-shaped ground reaction force. If you're walking up the stairs, then you're able to capture the change in gait, where you're seeing that the entire foot is landing on the ground at a similar time. We've done some work where we've integrated these sensors into prosthetics, and then we are doing load monitoring for that. We've developed flexible sensors where I'm wearing the sensors on the knee, and every time I sit down, I'm bending the knee, and so you can see a very high change in resistance. Or in this case, on the right, I'm wearing it on the elbow, and you can see that the change in resistance is proportional to the amount of bending at my elbow. So we can then monitor range of motion using these type of things. And these are so sensitive that if I'm wearing it on my finger and just writing the word, you can see as I bend my finger, we're picking up signals very effectively. And so if I then evaluate that, you can see that the two A's that I write in Delaware have similar signals. So there's some work ongoing with computer science department where we are using machine learning for human computer interaction type of work. So with that, I'll just like to acknowledge the funding agencies, a lot of my collaborators, Eric Thorstensen, Jill Higginson, Matt Murillo, and then all the wonderful students and postdocs that work with me. So I'll take any questions